Welcome back to the next video, everybody. Today we're going to look at L functions and the notion of modularity. So let's get into it. Let's let K be a natural number and let's let P be a prime. Let's let E over Q be an elliptic curve. We're going to define A sub P to the K of E to be P to the K plus 1 minus the number of points on the reduction of E mod P with coordinates in the field with P to the K elements F sub P to the K. Okay, so again, this quantity is the number of Fp to the K solutions to the reduction E tilde of a global minimal model of E mod P, let's say. In general, we'll define the A sub n of E's multiplicatively. So we'll say that A sub mn of E is A sub n of E times A sub m of E if m and n are coprime. Okay, so using the fundamental theorem of arithmetic, you should be able then to define A sub n of E for any natural number n. All right, so what's going on here? These guys are sort of recording the number of solutions on the reduction of E mod P over the field Fp to the K. So why is this extra P to the K plus 1 here? So I'll talk about that just for a minute. Let's suppose K is 1 for simplicity. Why am I subtracting the number of Fp points on E tilde sub P from P plus 1? That's because that's the same thing as subtracting the solution count working in Z mod PZ from P. And why would I do that? Well, I expect like my Weierstrass equation mod P to have two solutions xy for roughly half of the values of x mod P because of the y squared on the left-hand side of the Weierstrass model, and no solutions for the other values because I'm expecting roughly half of my outputs to be squares mod P and the other half not to be. Okay, so if you do the arithmetic and add all that up, you expect P points plus the point at infinity. So this means the estimated value of the number of Fp points on E tilde sub P should be P plus 1, these P points plus the point at infinity, right? So then what's APE measuring? It's just measuring the difference between the actual value and this estimate, which is P plus 1. So it's like an error term, basically. Okay. All right, zeta functions. Let's let P be a prime at which E has good reduction. The zeta function of E tilde sub P, so the subscript P here emphasizes the reduction of E mod P, is the formal power series Z of E tilde sub P over Fp with variable T. It's given by X, which is the formal power series for the exponential, of the sum from n equals 1 to infinity of the number of Fp to the n points on E tilde sub P times T to the n over n. And due to nice properties of logarithmic differentiation in geometric series, this is just a convenient way to store all the information about solutions over all finite field extensions of Fp of our reduced elliptic curve. Okay, so one prime at a time, one zeta function per prime of good reduction. All right. In Silverman 1, chapter 5, it's actually shown that the zeta function is a rational function of t. In fact, z of E tilde sub P over Fp with variable t is just Lp of t over 1 minus t times 1 minus pt, where Lp of t is 1 minus apt plus pt squared, so that's a polynomial with integer coefficients. And the AP here is the same thing as the AP from the first slide of this video, P plus 1 minus the number of Fp points on E tilde sub P. Okay, how about other primes? Primes not of good reduction. Well, if you want to extend the definition of LPT, these LPTs are called the local L factors at P. So if you want to extend the definition of the local L factor at P of t to include primes at which E has bad reduction, the proper way to go about it is to set Lp of t to be 1 minus t if E has split multiplicative reduction at P, 1 plus t if E has non-split multiplicative reduction at P, and 1 if E has additive reduction at P. There are various reasons this is correct. The reason that'll give you here is, in all cases, it turns out Lp of 1 over P is the number of Fp solutions on the non-singular locus of the reduction of E mod P divided by P. For that, you can see Washington's elliptic curves, number theory, and cryptography, section 2.10 for a proof of that, although that's not hard to prove. But there are other reasons. Look, you can, this isn't really the way even that's correct to define L functions. You can define all this using Galois representations, and then I think it all becomes much more natural, although a little bit more obtuse, because you can define all this using just the determinant of the image of Frobenius at P, okay, and using the inertia group. So I won't go into that, but there's kind of a much broader framework that all of this sits inside. All right, but this is a little bit more concrete and clean cut. So, all right, so what is the L function of E over Q? Well, the zeta functions are just taking care of what happens mod P for 1 prime P at a time, right? The L function of E over Q seeks to encompass information about all zeta functions at once. And so what you do is you define it to be L of ES, and it's the product over the primes P of the local L factors L sub P, evaluated at P to the negative S, and then you take the reciprocal. Okay. Now the substitution where you plug in P to the negative S for T here is motivated by basic properties of the Riemann zeta function that I won't go into. Okay. Now this is a nicer object than it initially looks, although it initially looks quite nice. If n is the conductor of E, let's set 1 sub E to be equal to 1 sub n, the trivial Dirichlet character mod n. Okay. The L function of E then turns out to have the Euler product given by the product over all primes P, 1 minus AP of E times P to the negative S, plus 1 sub E of P times P to the 1 minus 2S, and then take the reciprocal. And if you multiply all this out, it's actually somewhat easy to see. It's a nice little exercise. This organizes itself into the Dirichlet series. L of ES equals the sum from n equals 1 to infinity of A sub n of E times n to the negative S. So in other words, you get nothing but the Dirichlet series with coefficients, the A sub n of E's that we defined on the first slide. And S is just a complex variable here. If you want to see proof of some of this stuff, I would look at Diamond and Sherman chapter 5. Also, Reed University has a document called the L function of an elliptic curve that talks about this in some detail. It follows from the Hasse-bound, which I'll cover next video, that this series converges absolutely and uniformly on compact subsets for a real part of S bigger than 3/2. Okay. Another place you might go to look for more information about all this would be Silverman 1, Appendix C, and then, as usual, Diamond and Sherman chapters 5 and 8. All right. So here's how I like to think of the L function personally. It's the Dirichlet series whose coefficients are these A sub n of E's from slide 1. All right. How about the L function of a new form, or more generally, a cusp form? For a new form F with Fourier coefficients A sub n and S2n, we can form the L function of F, and it's just the Dirichlet series, L of Fs, which is the sum from n equals 1 to infinity of A sub n times n to the negative S. So again, you just make the Dirichlet series, whose coefficients are the Fourier coefficients of F. That's all you do. This converges absolutely and uniformly on compact subsets on the real part of S bigger than 2. More generally, if F is a cusp form of weight K, this will converge absolutely and uniformly on compact subsets on the real part of S bigger than K over 2 plus 1. Okay, so you can see DS chapter 5 for a proof of this. So a conjecture, a theorem, and then a definition. Temporary conjecture, what do we like? L functions, they're a lot easier to work with when they're defined everywhere, not just on right half planes. They're also a lot easier to work with when they have functional equations, because then we can just sort of study them by studying them on a thin vertical strip, usually. Okay, so temporary conjecture, let's let E over Q be an elliptic curve. Then the L function of E has an analytic continuation to all of C and a functional equation relating its values at S and 2 minus S. Perfect, if that's true. That's exactly what I wanted. Theorem. LFS has an analytic continuation to C and has such a functional equation. This is proven in Diamond and Sherman chapter 5. Huh. Interesting. If only there was a way to think about elliptic curves in terms of modular forms and vice versa, then I could port this fact over to that conjecture up here and turn the conjecture into a theorem, right? Well, that motivates, well, that's one of the motivating definitions for the modularity of an elliptic curve. We say an elliptic curve E over Q with conductor N sub E is modular if there's a new form F with trivial Nabentypus. So in other words, it's in S2 of gamma 0 N sub E. Such that the L function of F matches the L function of E. Although it turns out really they only need to match it. Their coefficients only need to match at primes of good reduction for them to match everywhere. The proof of that would be discussed in Diamond and Sherman in the later chapters if you want to see that. Okay, but you don't really need to worry about that. You're modular if there's a new form with trivial character with conductor, the conductor of the elliptic curve. Let's call that new form F, such that the L function of F matches the L function of E. Okay, so if E over Q is modular, then because of theorem 3, our temporary conjecture just holds, right? Our L function of E will have that analytic continuation and that functional equation we are after. If every elliptic curve over the rationals is modular, that means the conjecture is just true for all elliptic curves E over Q. And there's a lot of reasons this is significant, but one of them is the famous Birchon-Swinnerton-Dyer conjecture, which is still open. This conjectures that the rank of an elliptic curve E over Q is the order of vanishing of LES at S equals 1. So why is this significant to that conjecture? If every elliptic curve E over Q is modular, you can say L of E1 exists at least for all elliptic curves E over Q. In other words, the Birch and Swinnerton-Dyer conjecture is well defined. You see, because you can't plug S into the L function of E if the L function of E is only defined for the real part of S bigger than 3/2. But if there's an analytic continuation, you can plug one into this, or more specifically into its analytic continuation. Okay, so there you go. That's what it means for an elliptic curve to be modular. And that's a little bit about why we care. Starting next video, we'll begin looking at a very important theorem that gives you, well, I'll give you 5 different equivalent ways of thinking about what it means for an elliptic curve to be modular, and I'll call it the 5-fold theorem. All right, so I will see you all tomorrow. Thanks for watching, and I'll see you then.